Behavior of waves, concept 2, notes. All right, let's get right into it. I'm going to kind of go fast, but that's why you're watching this on your own, so you can pause it as much as you need. We're talking about the different behaviors that waves all have, and this really ties in exactly with the stations that you were doing last Friday. You had 6 different stations to go to, 6 different activities to do, and that will correspond with the 6 things I'm going to go over. So what you should think about as I go over this today is which station goes with each concept. So for example, reflection, think in your head, which station that you went through actually was showing reflection. Okay, reflection, you guys have all seen images that are beautiful, like this one on the bottom showing reflection. Here's the definition. It is when a wave strikes an object and bounces off of it. All waves do this. And a sound wave, think for a moment, what happens when a sound wave is reflected? Hopefully you thought of it, that's an echo. But mostly when we think about reflection, we're thinking about light waves. There is a law of reflection that you should know, and I'll explain this pretty fast. This is that the angle of incidence is always equal to the angle of reflection. So take a look at this picture down at the bottom. We have an angle coming in. This would be like a light wave or a sound wave going off to hit the reflecting surface. So for example, maybe that is water or a mirror. And there's the incident ray, so the wave that strikes the surface. Now, after it hits the reflecting surface, it's going to create a reflected ray. That's the wave that bounces off of the surface. And the rule says, just like I already read, that the angle of incidence, shown right here, is equal to the angle of reflection. And when we talk about the angle that it makes, that's the angle of the ray compared to the normal line, which is that dotted line shown right here. The normal line is a line perpendicular to the reflecting surface. And so, for example, if the angle of incidence is 30 degrees, then the angle of reflection would also be 30 degrees. This is true, again, of all waves. This is the law of reflection. It always holds true. Okay, next concept, refraction. Again, think about where you may have seen this in the station activity. Okay, that fish looks kind of interesting, right? Does that fish have 2 tails? Okay, obviously not. You guys have all seen this before. Now, why does it look like the fish has 2 tails? The reason is because of refraction. Refraction is the bending of waves caused by a change in its speed as it moves from one medium through another. So in this example of the fish, the 2 mediums that in this situation light waves are traveling through would be air and water. And as the light waves move from the air into the water, it changes speed. We actually talked about this in concept 1. Light waves move at different speeds depending on the medium that they're in. The greater the change in speed, the more the wave bends. So, for example, let's pretend for a moment that instead of water, this fish is in jelly or jello. And that's a solid. And so if the fish was in that kind of a medium, then this would actually be even greater of a bend. The fish's body would actually be more at this kind of an angle instead of this angle. Because there's a greater change in speed when light waves move from air into a solid as opposed to from air to a liquid. And this actually relates to how prisms work. You may have seen a prism before. It is usually a glass triangle kind of shape. And what happens is that if you hold it up to the light, a rainbow will shine through. And so let me start maybe from what the slides say. Okay, light waves enter into a prism and slow down due to the change in medium. So again, here on the left-hand side, a light wave is entering into the prism. And now this is a change in medium because this is a solid and it was just in a gas. And that causes the light wave to bend and it creates all of these different colors. Now, why do we get different colors that come through it? Well, they bend different amounts. The different light waves bend different amounts, and that's due to their wavelength. Each color of light has a different wavelength. So, for example, red has the longest wavelength. Violet has the shortest wavelength, and that's why they travel at different speeds. These 2 concepts I just talked about, this one over here, those are not extremely important for you to know. That's just kind of an intro to what we'll talk about later on this week. So when we look at rainbows in the sky and how they're formed, what's actually happening is that there are little water droplets in the air. And as light passes from the air into those water droplets, it changes medium. It goes from the gas into a liquid, and that causes the light wave to refract, to bend, and to create those different colors that you see in the sky. Next one is diffraction. Diffraction is when an object causes a wave to change direction and bend around it. So take a look at these two diagrams. Here, these straight blue lines are light waves, and they're approaching, let's pretend that this is a building. Okay, this is a building, and this is a window. As they move through that, they have to bend in order to go through that window. And so you can see there's two different pictures here. In one of them, the window is rather small. The other one, the window is rather large. When the space is larger, the waves don't have to bend as much in order to get through it. So, amount of diffraction depends on the size of the object the waves hit. You can see here again how that affects it. And then the wavelength of the waves. For example, sound waves tend to diffract much better than light waves because they are much larger. Now think about if you're in your house. Pretend, maybe your house is actually like this, I don't know. Pretend your bedroom is in the back of the house, and then your bathroom is down the hall. If you were to turn on the light in your bedroom and your door was open, it would travel out into the hallway and it might reach your bathroom. But if you were to say something from your bedroom, maybe yell to your mom or dad, then that sound wave would travel much easier throughout the entire house, including the bathroom. So to sum up, sound waves travel much better around obstacles and through different objects as when you compare it to light waves. Here are some real life examples of diffraction. So we have light coming in through a window, and it has had to bend to get through the window, but once it gets through the window, it spreads out. Same thing is true for these clouds. Next up is absorption. Okay, absorption is when a wave strikes an object and goes into it. In other words, it's absorbed. When that happens, energy from the wave gets converted to thermal energy. That means heat energy. This is why in the summer, many times people will say you should not wear darker colors, or I'm sure you've experienced this. If you wear a darker t-shirt, then you'll feel hotter outside as opposed to if you're wearing like a white t-shirt or a lighter colored t-shirt, because dark colors are better absorbers of light waves. And so when you're wearing a black t-shirt, it absorbs the sun's light waves and then converts it to thermal energy or heat on your body. But if we lived in a cold climate, wearing a dark jacket would be a good idea to keep you warmer, a little bit easier. Okay, a couple more. Interference is the next one. Interference is when two or more waves combine to form a new wave, and it can be constructive or destructive. So constructive interference, when you hear that word constructive, you should think about the word construct, or to build or to make. So this is when two or more waves add together. They're going to build something newer and better. Not better, bigger. Okay, like parts of waves must line up in this. So if you look at the diagram below, if we have this wave plus this wave, we will get this wave. But they have to be lined up. So the two troughs are aligned, the crests, troughs, crest. And that will make a wave that is twice the size. It's an increase in amplitude. It can also be destructive. Destructive, tear it down, and you can see that's the final result here. If you look at the bottom, you have a flat line. You have no wave when you have a destructive interference. So they subtract from one another when they overlap. You can see here the trough and the crest are combined, crest and trough, so on and so forth. Last one, I'll go over this very fast. Resonance, a lot of you had fun with the tuning forks. I will actually show you more of this in class, but a quick definition for you to write down. This is the process where an object is made to vibrate at its natural frequency by absorbing the energy of another object that is vibrating at the same frequency. Again, I'll show you this more in class. This is a really cool concept. But yeah, example would be tuning forks for that. All right, it's time for a little bit of practice, and I will explain some more things to you in class.